The growth and decay model that we looked at yesterday is basically the two-unit idea. It's a very simple model. We're now going to look at the extension 1 model. It still is a simple model, but takes into account some external conditions. Right? So external conditions, the idea being that whilst a temperature of something would cool down if once you take it out of the oven, that actual temperature, well, it's not going to go down to 0. It can't go past the temperature of the room. So there's external factors involved. So this idea takes into account that sort of thing. So the differential equation is now not a constant times the population or temperature, if I was talking about that cooling one. It's actually the population minus some factor, some external factor. The solution, again, just like yesterday's, you don't have to derive the solution. But we would do it exactly the same as we did yesterday. I'd turn that upside down so it's with respect to P and integrate and so on. There actually are two solutions. The first solution is that P equals N. That's what we call a trivial case, and we don't consider it. Because if you look at it logically, if P was equal to N, then the derivative would be 0. And clearly, if you differentiate a constant, you get 0. So it does work, but it's not a very interesting case to look at. The solution we're interested in is this one. So it is our basic one that we saw yesterday, some constant times e to the kt, but plus some external condition. If you think of the graph, we have an exponential curve that's been shifted up n. So that is that external condition. So the graph is not now going towards 0, it's going towards, well, the room temperature or whatever the external condition would be. So P still stands for population or temperature or whatever it is you're measuring. The initial population now would be N plus A, not just A. Again, you can see it from, if you substitute in T equals 0, you can clearly see, well, e to the power of 0 is 1, you get N plus A. So the initial population is now N plus A. K is still our growth or decay if it turns out to be negative. And T, of course, is still time. All right, well, let's look at a classical question. Newton's law of course, Newton, he does everything. 1993, woo, long time ago. Let T be the temperature, so that's the actual temperature we're measuring inside a room at any particular time. Little t, A is the constant outside air temperature. Newton's law of cooling states that the rate of change of temperature is proportional to T minus A. Show that T equals A plus C equals KT satisfies this. So much like yesterday, we don't have to go through and turn the derivative upside down, use logs and all that. We just differentiate this and shows it satisfies the P to T equals what we want. So T is equal to A plus C e to the KT. Differentiate that, well, differentiate A, you get 0, of course, because A is a constant. KC e to the KT, but remember, we're trying to show it's K times this T minus A. It's proportional to T minus A. Well, T minus A is, in fact, C e to the KT, because if you look at the original equation, if I just move the A to the other side, I get T minus A is C e to the KT. So we have dt is K T minus A. So it satisfies our differential equation of dt is some constant times T minus A. So that's all we have to do to show that it satisfies. All right, so the outside air temperature is 5 degrees Celsius. Heating system breakdown causes the inside room temperature to drop from 20 to 17 in half an hour. How long or after how many hours is it going to take to get down to 10 degrees? Okay, well, T will equal 5 plus C e to the KT. Remember they told us that A, was it A that they used? Yeah, was the outside air temperature, which we've been told now is 5. So therefore C is 15, because when T equals 0, initial temperature is 20. So I now have the formula 5 plus 15 e to the KT. I'm now going to have to work out the decay rate. So the other piece of information they've told me, where is it? Half an hour. So when time is half an hour, so time is 0.5, the temperature's dropped to 17. So now we just make K the subject. Move some terms around, divide by 15. So 0.5 K is a log of 12 on 15. So K is 2 log 12 on 15. So that's the exact value that we use in any subsequent calculation. We now want to know when is the temperature equal to 10. So 10 equals 5 plus 15e to the KT. And eventually, after playing around and making little t the subject, I get 1 on K, that number we've stored in our calculator, the log of a third, which is 2.46167, and I'm sure there's more numbers after that. So 2.5 hours. So after 2.5 hours. Okay. So really, that's the only difference between what we were doing yesterday, is we've just added this external condition to the problem. Okay.